Right now, as you read this sentence, every atom in your body is being pulled toward the center of Earth with a force so relentless that nothing can escape it. Gravity is supposedly the weakest of the four fundamental forces, yet it's powerful enough to hold together galaxies spanning hundreds of thousands of light years. It carved the cosmic web itself, clustering matter into the magnificent structures we observe throughout the universe. For over 300 years since Newton first described it, we've understood gravity as the great cosmic gatherer, the force that pulls everything together. But here's what makes this deeply disturbing. Our universe is not contracting under gravity's influence. It's expanding. Not just expanding, but accelerating its expansion at a rate that should be impossible if gravity truly rules the cosmos. In 1998, two independent teams of astronomers made measurements that shattered our understanding of reality. They discovered that galaxies aren't just moving away from us. They're moving away faster and faster, as if some invisible force is overpowering gravity itself and literally ripping spacetime apart. We thought we lived in a universe where matter attracted matter, where cosmic structures grew larger and denser over time, where eventually everything would collapse back together in a final gravitational embrace. We were completely wrong. Instead, we inhabit a cosmos dominated by something we cannot see, cannot touch, and cannot understand. A mysterious energy that comprises 68% of everything that exists, and is actively working against the very force we thought controlled the universe. Tonight, we're going to explore the most profound paradox in modern physics. How can gravity pull everything together while the universe simultaneously expands apart? The answer will take us from Einstein's greatest mistake to the discovery of dark energy, from the quantum foam of empty space to the ultimate fate of every star, planet, and particle in existence. You'll discover why the space between galaxies is growing larger every second, what this means for the future of life itself, and how this cosmic tug-of-war determines whether our universe ends in ice, fire, or something far stranger. The question that haunts every cosmologist is this: what force could possibly be stronger than gravity on the largest scales? The answer challenges everything we thought we knew about the nature of reality itself. For decades after Einstein published his theory of general relativity in 1915, physicists assumed the universe was static and eternal. Einstein himself was so convinced of this that he added a cosmological constant to his equations, essentially an anti-gravity term to balance out gravitational attraction and keep the cosmos stable. But in 1929, Edwin Hubble, peering through the 100-inch telescope at Mount Wilson Observatory, made observations that changed everything. He discovered that distant galaxies were moving away from us, and the farther away they were, the faster they were receding. This revelation should have settled the matter. If the universe was expanding from some initial state, then gravity should be slowing that expansion down, like a ball thrown upward, eventually succumbing to Earth's gravitational pull. Every cosmologist predicted that measurements of distant supernovas would reveal a universe whose expansion was gradually decelerating. The only question was whether gravity was strong enough to eventually halt the expansion entirely and cause a big crunch, or whether the universe would expand forever, but at an ever-slowing rate. But reality had other plans. When the Supernova Cosmology Project and the High-Z Supernova Search Team independently measured the brightness of type Ia supernovas in distant galaxies, they found something that should have been impossible. These cosmic explosions, which serve as standard candles for measuring astronomical distances, appeared dimmer than expected. This could only mean one thing. The galaxies containing them were farther away than predicted by models of a decelerating universe. The universe wasn't slowing down. It was speeding up. Subscribe and hit that thumbs up if you've ever wondered how the fundamental forces actually work at cosmic scales. And here is a question that will haunt you. If something is overpowering gravity throughout the entire universe, what does that mean for the ultimate fate of everything you love? Drop your thoughts in the comments. I'll pin the most mind-bending answer. This discovery earned Saul Perlmutter, Brian Schmidt, and Adam Rees the 2011 Nobel Prize in Physics, but it also created the greatest mystery in modern science. We now know that approximately 68% of the universe consists of dark energy, a form of energy that permeates all of space and exerts a negative pressure, effectively pushing spacetime apart. But we have no idea what it actually is, where it comes from, or why it exists. What we're about to explore together will fundamentally change how you see the cosmos around you. We'll discover how empty space itself might possess energy, why the universe's expansion is accelerating rather than slowing down, and what this cosmic acceleration means for the survival of stars, planets, and life itself in the far future. You will learn about the delicate balance between attraction and repulsion that determines the structure of everything from solar systems to galaxy clusters, and why this balance is shifting in favor of forces we barely understand. Most remarkably, you'll discover that this isn't just an abstract cosmic phenomenon. It's happening right here, right now, in the space between you and your screen. Every cubic meter of seemingly empty space around you contains enough dark energy to power a small city. Yet this energy is so evenly distributed that we can't directly detect it except through its effects on the largest scales of the universe. Now, let us begin our journey into the cosmic tug-of-war that is determining the fate of everything that exists. Chapter 1. Cosmic Forces. Every force in the universe tells a story of attraction or repulsion, of things coming together or being pushed apart. But gravity has always been special. Unlike the electromagnetic force that can both attract and repel depending on charge, or the strong nuclear force that only operates at subatomic distances, gravity seemed elegantly simple. It only attracts, and it affects everything that has mass or energy. When Isaac Newton first formulated his law of universal gravitation in 1687, he described a cosmos where every particle of matter attracts every other particle with a force proportional to their masses and inversely proportional to the square of the distance between them. This wasn't just mathematics, it was poetry written in the language of physics. The same force that makes an apple fall from a tree keeps the moon in orbit around Earth, holds our planet in orbit around the sun, and binds our solar system within the Milky Way galaxy. For over 2 centuries, this picture seemed complete. Gravity was the architect of cosmic structure, the great cosmic sculptor that shaped everything from planetary orbits to the spiral arms of galaxies. Astronomers could predict the motions of comets decades in advance, discover new planets by observing gravitational perturbations, and explain the tides through lunar gravitational influence. The universe appeared to be a vast clockwork mechanism, with gravity as its primary driving force. But the story becomes far more complex when we zoom out to cosmic scales. In the early 20th century, Einstein's theory of general relativity revealed that gravity isn't actually a force in the traditional sense. It is the curvature of space-time itself. Massive objects don't pull on other objects. Instead, they warp the fabric of space and time, and objects follow the straightest possible paths through this curved geometry. Imagine placing a bowling ball on a stretched rubber sheet. The ball creates a depression, and smaller objects rolled nearby will curve toward it not because of any mysterious pulling force, but because they're following the curved surface. This geometric understanding of gravity explained phenomena that Newton's theory couldn't account for, such as the precise orbit of Mercury and the bending of light around massive objects. More importantly, it provided a framework for understanding the universe as a whole. Einstein's field equations describe how the distribution of matter and energy determines the curvature of spacetime, and how this curvature influences the motion of everything within it. When astronomers first applied these equations to the entire universe, they made a startling prediction. The cosmos could not be static. If matter is distributed throughout space, then gravity should either cause the universe to collapse in on itself or expand outward from some initial state. There was no stable, eternal universe in Einstein's mathematics, only dynamic ones that either contracted or expanded. Einstein himself was troubled by this implication. Like most physicists of his era, he believed in an eternal, unchanging cosmos. So he modified his equations by adding what he called the cosmological constant, a term representing a repulsive force inherent in space itself that could exactly balance gravitational attraction and maintain a static universe. It was a mathematically elegant solution, but it required introducing a new fundamental property of empty space, the ability to push things apart. This modification troubled Einstein deeply, because cosmological constants seemed arbitrary, a mathematical trick rather than a fundamental insight into nature. He later called it his greatest mistake when Edwin Hubble's observations revealed that the universe was indeed expanding, apparently making the cosmological constant unnecessary. But here's where the story takes a fascinating turn. Hubble's discovery of cosmic expansion didn't eliminate the mystery of competing forces. It deepened it. If the universe began expanding from some initial state, then gravity should be working constantly to slow that expansion down. Every galaxy should be pulling on every other galaxy, gradually reducing the rate at which they move apart. The question that dominated cosmology for the next 70 years was simple. Is gravity strong enough to eventually halt the expansion and cause the universe to collapse, or will the universe expand forever with gravity merely slowing the expansion rate? This wasn't just an academic question. It determined the ultimate fate of everything in existence. To understand why this matters, consider what happens in each scenario. In a closed universe where gravity eventually wins, the expansion would halt and reverse, leading to a big crunch where all matter and energy collapse back together. In an open universe where expansion continues forever, stars would eventually burn out, black holes would evaporate through Hawking radiation, and the cosmos would end in a cold, dark, empty state called heat death. Both scenarios assumed that gravity was the dominant force on cosmic scales. The only variable was whether there was enough matter in the universe to generate sufficient gravitational attraction to halt the expansion. Astronomers spent decades trying to measure the total mass density of the universe to determine which fate awaited us. They counted stars, measured the mass of gas clouds, estimated the amount of dark matter needed to explain galactic rotation curves, and calculated the mass required to form the cosmic web of filaments and voids we observe. Every measurement seemed to suggest that the universe didn't have quite enough matter to halt its expansion. It would continue expanding forever, but at a gradually decreasing rate, as gravity slowly won the long-term battle against cosmic expansion. This understanding dominated cosmology until 1998, when two independent research teams set out to measure exactly how much the universe's expansion was slowing down. They planned to use Type Ia supernovae stellar explosions that always reach approximately the same peak brightness as standard candles to measure precise distances to galaxies billions of light years away. By comparing these distances to the redshift of the galaxies, they could determine how the expansion rate had changed over cosmic time. What they discovered defied every prediction and challenged our fundamental understanding of cosmic forces. The universe's expansion wasn't slowing down at all. It was accelerating, as if some unknown force was overpowering gravity on the largest scales and actively driving galaxies apart at an ever-increasing rate. This revelation demanded a complete revision of our cosmic inventory. If 68% of the universe consists of dark energy that causes accelerated expansion, and another 27% is dark matter that we can't directly detect, then the ordinary matter that makes up stars, planets, and everything we can see comprises less than 5% of total cosmic content. We live in a universe dominated by forces and forms of matter we don't understand. But perhaps most remarkably, this discovery suggested that Einstein's greatest mistake, the cosmological constant, might have been his greatest insight. The universe does indeed seem to possess an inherent property of space itself that causes repulsion on cosmic scales. Whether this is Einstein's cosmological constant, some form of dynamic dark energy, or something even more exotic, remains one of the greatest unsolved mysteries in physics. What we've uncovered reveals that the cosmic tug-of-war between attraction and repulsion operates on multiple scales, simultaneously, with different forces dominating at different sizes and distances. Chapter 2. Hidden Energy. The space around you appears empty, but appearances can be profoundly deceiving. Every cubic meter of what we call vacuum seethes with quantum activity, virtual particles popping into existence and annihilating each other in timeframes so brief they exist below the threshold of direct measurement. This quantum foam represents one of the most counterintuitive aspects of modern physics. Empty space isn't empty at all, but filled with energy that might be driving the universe's accelerated expansion. When Werner Heisenberg formulated his uncertainty principle in 1927, he revealed that even in perfect vacuum, energy cannot be exactly zero. The more precisely you try to define the energy state of empty space, the more uncertain it becomes, leading to quantum fluctuations that give the vacuum an irreducible minimum energy density. These vacuum fluctuations aren't just theoretical constructs. They produce measurable effects like the Casimir force, where two metal plates placed extremely close together in vacuum experience an attractive force due to the difference in quantum field energy between them and the surrounding space. The question that haunts cosmologists is this: if empty space possesses vacuum energy, and if Einstein's equations tell us that all forms of energy contribute to space-time curvature, then why doesn't this vacuum energy cause the universe to expand at rates trillions of times faster than observed? When physicists calculate the expected energy density of quantum vacuum fluctuations, they get a number so large that it would cause space to expand so rapidly that atoms couldn't form, let alone stars and galaxies. This is called the cosmological constant problem, and it represents perhaps the most severe mismatch between theoretical prediction and experimental observation in the history of physics. The quantum field theory prediction for vacuum energy density exceeds the observationally determined value by a factor of 10,120, a number so large that it defies comprehension. If theoretical physics were off by even a factor of 10 in predicting something as fundamental as the energy of empty space, it would be considered a major crisis. Being off by 120 orders of magnitude suggests we're missing something profound about the nature of reality itself. Yet despite this theoretical catastrophe, we know observationally that empty space does possess some form of energy that's causing cosmic acceleration. When astronomers measure the expansion history of the universe through observations of distant supernovas, cosmic microwave background radiation, and the large-scale structure of galaxies, they find consistent evidence for a dark energy component with very specific properties. Dark energy appears to have a constant density throughout space and time. As the universe expands and the volume of space increases, the total amount of dark energy increases proportionally to maintain the same energy per cubic meter. This is radically different from matter, which becomes more dilute as space expands. It's as if space itself possesses an intrinsic energy that scales with volume rather than being carried by particles or fields that can be dispersed. Moreover, dark energy exhibits negative pressure, meaning it doesn't just resist compression like normal matter. It actively pushes outward on the boundaries of any region containing it. In Einstein's equations, this negative pressure contributes to gravitational effects with the opposite sign of normal matter and energy. While matter and radiation cause space-time to curve in ways that bring objects together, negative pressure causes space-time to curve in ways that drive objects apart. The Wilkinson Microwave Anisotropy Probe, launched in 2001, provided the most precise measurements of cosmic composition to date. By analyzing tiny temperature fluctuations in the cosmic microwave background, the afterglow of the Big Bang, scientists determined that dark energy comprises approximately 68.3% of the universe's total energy density. This measurement agrees remarkably well with supernova distance measurements and observations of how galaxy clusters have evolved over cosmic time. But knowing that dark energy exists and measuring its effects doesn't tell us what it actually is. The simplest explanation is that it represents Einstein's cosmological constant, a fixed energy density inherent in space itself that never changes as the universe evolves. This would mean that every cubic meter of empty space contains exactly the same amount of dark energy today as it did when the first stars formed, and as it will billions of years in the future. Alternative theories propose that dark energy might be dynamic, changing its properties over cosmic time. These quintessence models suggest that dark energy could be a slowly evolving field similar to the fields that drove cosmic inflation immediately after the Big Bang. Unlike the cosmological constant, quintessence could strengthen or weaken over time, potentially leading to very different cosmic futures than those predicted by a static dark energy density. Some physicists speculate that dark energy might emerge from modifications to gravity itself on cosmic scales. These modified gravity theories propose that Einstein's general relativity, while extremely accurate for describing solar system physics and stellar dynamics, might break down when applied to the entire observable universe. In these models, what we interpret as dark energy could actually be a signature of new gravitational physics that only becomes apparent at distances of billions of light years. The implications of each possibility are profound. If dark energy is Einstein's cosmological constant, then its effects will persist unchanged for eternity, driving the universe toward a cold, dark future where galaxies become isolated islands in an ever-expanding sea of empty space. If dark energy weakens over time, gravity might eventually regain dominance, potentially leading to a future cosmic collapse. If it strengthens, the acceleration could increase until it overwhelms all our forces, literally tearing apart stars, planets, and even atomic nuclei in a catastrophic Big Rip. Current observations suggest that dark energy has remained remarkably constant over the past several billion years, but detecting small changes requires measurements of extraordinary precision across vast cosmic distances and timescales. The Dark Energy Survey, which concluded in 2019 after mapping over 300 million galaxies, found no evidence for significant evolution in dark energy properties, supporting the cosmological constant interpretation. Yet the mystery deepens when we consider that the observed value of dark energy appears to be precisely tuned to allow the formation of cosmic structure. If dark energy were much larger, it would have prevented galaxies from forming in the early universe. If it were much smaller, it would have no observable effects today. The fact that we observe dark energy to have just the right strength to become dominant at approximately the same epoch when complex structures like solar systems and planets developed seems like an extraordinary coincidence. This coincidence problem suggests that either we're living at a special moment in cosmic history, or there's some deeper principle that determines the strength of dark energy in relation to matter density. Some theories propose that dark energy and matter are connected through mechanisms we don't yet understand, while others suggest that we might inhabit a multiverse where different regions have different dark energy densities, and we find ourselves in a region compatible with the existence of observers. What remains clear is that the energy hidden in empty space represents the dominant component of our universe, and its properties will determine the ultimate fate of everything we can see. This invisible energy that fills every corner of space is actively reshaping the cosmos on the largest scales. overpowering the gravitational attraction that built the stars and galaxies in the first place. The question that confronts us next is how this cosmic acceleration actually works. What mechanism allows dark energy to overwhelm gravity's influence and drive the universe toward an ever faster expansion? Chapter 3. Impossible escape. Imagine trying to escape from a gravitational well so deep that even light cannot climb out of it. This is the reality inside a black hole's event horizon, where gravity becomes so intense that it warps spacetime beyond the point of no return. Yet across cosmic distances, something is achieving what seems impossible, overpowering this same gravitational force that can trap light itself and driving the universe toward ever faster expansion. To understand how extraordinary this is, consider the strength of gravity in different contexts. On Earth, you need to reach a velocity of 11.2 kilometers per second, about 25,000 miles per hour, to overcome our planet's gravitational pull and escape into space. For the Sun, the escape velocity rises to 617 kilometers per second. For the supermassive black hole at the center of our galaxy, which contains over 4 million solar masses compressed into a region smaller than Mercury's orbit, the escape velocity at the event horizon reaches the speed of light itself. This is why black holes represent the ultimate triumph of gravitational attraction. Not even electromagnetic radiation, which carries no mass and travels at the universe's speed limit, can escape once it crosses the event horizon. The curvature of spacetime becomes so extreme that all possible paths lead inward toward the central singularity. Einstein's equations describe this condition mathematically, but the physical reality defies intuition. Gravity literally breaks spacetime itself at the event horizon. Yet on cosmic scales, dark energy is accomplishing something that seems even more impossible than escaping from a black hole. It's not just overcoming gravity in isolated regions of space. It's overwhelming the cumulative gravitational effect of every galaxy, star, planet, and particle in the observable universe simultaneously. The total mass energy contained within our cosmic horizon is approximately 1,054 kilograms. That is roughly 100 trillion kilograms of matter and energy, all exerting gravitational attraction that should be working to slow cosmic expansion. To put this in perspective, imagine if every atom in your body was simultaneously trying to pull you in different directions, but some invisible force was strong enough to overcome all of these attractions combined and accelerate you away from everything else. This is essentially what is happening to every galaxy in the universe. They are being pushed apart by dark energy despite the gravitational attraction from literally everything else that exists. The mechanism by which this cosmic escape occurs challenges our understanding of how forces operate. In classical physics, forces act between objects. Gravity pulls masses together. Electromagnetic forces push charges apart or pull them together depending on their signs. And nuclear forces bind particles within atomic nuclei. But dark energy doesn't seem to act between objects at all. Instead, it appears to be a property of space itself that becomes stronger as space expands. This creates a feedback loop unlike anything else in physics. As dark energy drives cosmic expansion, it creates more space, which contains more dark energy, which drives faster expansion, which creates even more space. It's as if the universe contains a self-reinforcing mechanism for its own dissolution, with the energy that powers this dissolution growing stronger as the process continues. The mathematics of this process reveal why dark energy's effects are only noticeable on the largest scales. The force per unit mass that dark energy exerts on any object is extraordinarily small, about 10 to 29 newtons per kilogram. To put this in human terms, dark energy exerts less force on your entire body than the gravitational attraction between you and a grain of sand sitting on the moon. Over the distance between Earth and the Sun, dark energy provides less acceleration than you'd get from a gentle breeze. But cosmic distances are vast beyond human comprehension. Over the 2.5 million light-year distance to the Andromeda Galaxy, dark energy's tiny acceleration accumulates to significant effects. Over the billions of light-years that separate galaxy clusters, this acceleration becomes the dominant force determining their motion. The universe is so large that even infinitesimally small accelerations, when integrated over cosmic distances and timescales, can overpower the strongest gravitational attractions. This scale dependence explains why we don't notice dark energy in our daily lives or even within our solar system. The gravitational binding energy of Earth's orbit around the Sun, or the Moon's orbit around Earth, is millions of times stronger than dark energy's influence over those distances. Dark energy is only winning the cosmic tug-of-war because it operates over such vast scales that its tiny but persistent acceleration can accumulate to overwhelming effects. The Hubble Space Telescope's observations of distant supernovas revealed exactly how this cosmic escape manifests observationally. When astronomers measure the light from Type Ia supernovas in galaxies billions of light years away, they're seeing these stellar explosions as they appear billions of years ago when the universe was smaller and younger. By comparing the apparent brightness of these standard candle explosions to their redshift, astronomers can determine how fast those galaxies were moving away from us at different epochs in cosmic history. What they found was that the universe's expansion has not been constant. For the first several billion years after the Big Bang, gravity was indeed winning the battle against cosmic expansion. The expansion rate was gradually decreasing as the gravitational attraction between galaxies slowed their recession from each other. But approximately 5 to 6 billion years ago, something changed. The expansion began accelerating as dark energy effects finally overcame the gravitational deceleration that had dominated earlier cosmic history. This transition point represents one of the most important moments in cosmic evolution. Before this epoch, gravity was the primary force shaping the large-scale structure of the universe. Galaxy clusters could form and grow as matter continued to collapse under gravitational attraction. After this point, dark energy began preventing the formation of new large-scale structures and started the process of gradually isolating existing galaxy clusters from each other. The Planck satellite's precise measurements of the cosmic microwave background confirmed this timeline through independent observations. By analyzing the pattern of temperature fluctuations in the universe's afterglow, cosmologists could trace the evolution of cosmic structure from the earliest epochs through the transition to dark energy domination. The data showed that dark energy effects were negligible in the early universe when matter density was much higher, but became increasingly important as cosmic expansion diluted matter while leaving dark energy density unchanged. This observational evidence reveals that cosmic escape isn't happening through some sudden, dramatic event, but through a gradual shift in the balance of forces. Dark energy has been present throughout cosmic history, but its effects only became noticeable when the universe expanded enough that matter density dropped below dark energy density. At that point, the cosmos crossed a threshold beyond which gravitational attraction could no longer compete with dark energy as repulsive effects. Looking toward the future, current models predict that this cosmic escape will continue accelerating indefinitely. As the universe expands and matter becomes even more dilute, dark energy's dominance will grow stronger. Galaxy clusters will become increasingly isolated as the space between them expands faster than light can travel. Eventually, the accelerated expansion will separate galaxies so far that beings living in one galaxy won't be able to observe any others, creating cosmic horizons beyond which no information can travel. The ultimate fate of this process depends on whether dark energy remains constant or evolves over time. If it's truly Einstein's cosmological constant, The acceleration will continue forever at roughly the current rate, leading to a cold, dark, empty universe in the far future. But if dark energy is a dynamic field that can change its properties, the cosmos might face more dramatic destinies, from renewed gravitational collapse to catastrophic acceleration that tears apart the fundamental structure of matter itself. What we're witnessing is the universe's ongoing escape from its own gravitational bonds, a process that will reshape the cosmos on scales and timescales that dwarf human comprehension. Chapter 4. Ancient Predictions. Long before astronomers discovered cosmic acceleration, the mathematics of general relativity contained hidden prophecies about the universe's fate. When Einstein first solved his field equations in 1917, he uncovered predictions so unsettling that he refused to believe them, leading him to modify his theory to preserve a static, eternal cosmos. Those original solutions described a universe that could not remain unchanged. It must either expand or contract under the influence of its own gravity. The story begins with a Russian mathematician named Alexander Friedmann, who in 1922 took Einstein's unmodified equations and applied them to a universe filled uniformly with matter and energy. Unlike Einstein, Friedmann was willing to accept whatever mathematical conclusions emerged, even if they challenged philosophical assumptions about cosmic permanence. His solutions described three possible universes: one that expanded forever, one that expanded to a maximum size before contracting, and one that oscillated between expansion and contraction cycles. These Friedmann models represented more than mathematical curiosities. They were the first rigorous predictions about cosmic evolution derived from fundamental physics. Each solution depended on a single parameter, the density of matter and energy compared to a critical value that would perfectly balance gravitational attraction against expansion. If the actual density exceeded this critical value, gravity would eventually halt expansion and cause universal collapse. If it fell below the critical value, expansion would continue forever with gradually decreasing speed. What makes these predictions remarkable is that they anticipated the discovery of cosmic expansion by 7 years. When Edwin Hubble announced his observations of galactic recession in 1929, he was essentially confirming what Einstein's mathematics had predicted all along. The universe described by general relativity was dynamic, not static, and its evolution was governed by the competition between gravitational attraction and the momentum of expansion. But Friedmann's models contained an implicit assumption that would later prove incorrect. They assumed that gravity was the only force affecting cosmic expansion on the largest scales. In these solutions, the expansion rate could only decrease over time as gravitational attraction gradually slowed the recession of galaxies. The question was not whether cosmic expansion would decelerate, but whether it would decelerate fast enough for gravity to eventually reverse the expansion entirely. The Belgian physicist Georges Lemaître independently discovered similar solutions and took the next crucial step in 1927. He proposed that if the universe was expanding, then extrapolating backward in time led to an initial moment when all matter and energy were concentrated in an extremely hot, dense state he called the primeval atom. This was the first scientific formulation of what we now call the Big Bang theory, derived directly from Einstein's equations applied to cosmic evolution. Lemaître also made another prescient prediction. He suggested that Einstein's cosmological constant, the term representing repulsive energy in empty space, might not be zero, even in an expanding universe. While Einstein had introduced this term to maintain cosmic stasis and later abandoned it when expansion was discovered, Lemaître realized that a small positive cosmological constant could explain observed discrepancies in the rate of cosmic expansion. These theoretical insights lay dormant for decades because astronomers lacked the observational tools to distinguish between different cosmic models. Throughout the mid-20th century, the primary goal of observational cosmology was simply to measure the current expansion rate, the Hubble constant, and determine whether the universe contained enough matter to eventually halt its expansion. The possibility that expansion might be accelerating seemed so unlikely that few astronomers even considered searching for it. The theoretical framework for understanding accelerated expansion existed in Einstein's original equations, but recognizing its significance required a conceptual leap that most physicists were reluctant to make. Einstein's cosmological constant represented energy inherent in space itself, a radical departure from conventional thinking about matter and energy as properties of particles and fields that existed within space. The idea that empty space could possess energy that affected cosmic evolution seemed too speculative to take seriously. This skepticism persisted even as quantum field theory developed throughout the mid-20th century and revealed that vacuum states are far from empty. Quantum mechanics predicts that virtual particle pairs continuously appear and annihilate in empty space, creating quantum fluctuations that should contribute to the energy density of the vacuum. But when physicists calculated the expected magnitude of this vacuum energy, they found it should cause cosmic acceleration trillions of times faster than observed, making the connection between quantum vacuum energy and dark energy seem impossible. The breakthrough came when astronomers realized they could test cosmic acceleration directly by measuring the expansion history of the universe. Type Ia supernovas provided the key observational tool because these stellar explosions always reach approximately the same peak brightness, allowing astronomers to determine precise distances to galaxies billions of light years away. By comparing these distance measurements to the redshift of the host galaxies, they could reconstruct how the expansion rate had changed over cosmic time. The Supernova Cosmology Project, led by Saul Perlmutter, began systematic observations of distant supernovas in the 1990s with the explicit goal of measuring cosmic deceleration. Their expectation was to determine how much the expansion had slowed down since the early universe, providing a direct measurement of the total matter density and settling the question of whether the universe would expand forever or eventually recollapse. Simultaneously, the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, pursued the same goal using slightly different observational strategies. Both teams expected to find evidence for deceleration. The only question was whether the deceleration was strong enough to eventually halt cosmic expansion. Neither team anticipated discovering that the universe's expansion was actually speeding up. When the first results became available in 1998, both teams initially assumed they had made systematic errors in their measurements. The data indicated that distant supernovas were dimmer than expected in a decelerating universe, implying that they were farther away than predicted by models where gravity gradually slowed cosmic expansion. This could only be explained if the expansion had been accelerating, driven by some form of energy that caused repulsion rather than attraction on cosmic scales. The statistical significance of the acceleration signal grew stronger as both teams accumulated more supernova observations. Cross-checks using different analysis methods, different samples of supernovas, and different approaches to systematic error correction all confirmed the same startling conclusion. Cosmic expansion has been accelerating for approximately the past 5 to 6 billion years, exactly as predicted by Einstein's equations with a positive cosmological constant. This discovery vindicated theoretical predictions that have been largely ignored for 8 decades. Einstein's greatest mistake turned out to be his greatest insight. The universe does indeed contain a cosmological constant, or something very similar to it, that drives accelerated expansion on cosmic scales. The same mathematical framework that predicted cosmic expansion from general relativity also contained the solution to the puzzle of why that expansion was accelerating rather than decelerating. But the vindication of old predictions also created new mysteries. While Einstein's equations accurately describe the effects of dark energy on cosmic expansion, they don't explain what dark energy actually is or why it has the specific value we observe. The cosmological constant that fits observational data is approximately 120 orders of magnitude, smaller than quantum field theory predictions for vacuum energy density, creating what many physicists consider the worst theoretical crisis in the history of science. Modern cosmology has thus fulfilled the ancient predictions of general relativity while simultaneously revealing the limitations of our understanding. We can describe the evolution of the universe with extraordinary precision using Einstein's equations, but we cannot explain the physical nature of the dark energy that dominates cosmic evolution. The mathematics anticipated the observations by nearly a century, yet the physics behind the mathematics remains as mysterious today as it was when Einstein first wrote down his field equations. The profound lesson is that the universe has been trying to tell us about its accelerating expansion since 1917, encoded in the mathematical structure of spacetime itself. It took human civilization 8 decades to develop the observational tools and theoretical sophistication to recognize what Einstein's equations had been predicting all along. Chapter 5. Quantum Mysteries. At the heart of the dark energy mystery lies one of the most profound disconnects in modern physics. The quantum vacuum should be seething with energy, yet somehow this energy either doesn't contribute to cosmic expansion or is precisely cancelled by unknown mechanisms to within 120 decimal places. This vacuum catastrophe, as physicists call it, represents our deepest ignorance about the fundamental nature of empty space and energy. Quantum field theory paints a picture of vacuum that would have seemed like pure fantasy to physicists a century ago. According to the uncertainty principle, energy and time are complementary quantities that cannot both be precisely determined simultaneously. This means that even in perfectly empty space, energy must fluctuate randomly on timescales so brief that the fluctuations exist below the threshold of direct observation. Virtual particles pop into existence in matter-antimatter pairs, exist for infinitesimal moments, and then annihilate each other and disappear. These quantum fluctuations aren't just theoretical constructs. They produce measurable effects in laboratory experiments. The Casimir effect demonstrates that when two perfectly conducting metal plates are placed extremely close together in vacuum, quantum fluctuations create a measurable attractive force between them. This occurs because the space between the plates can only support quantum waves with wavelengths that fit exactly between the boundaries, while the surrounding vacuum supports fluctuations of all wavelengths. The pressure difference creates a tiny but detectable force that pushes the plates together. Dutch physicist Hendrik Casimir calculated this effect in 1948, and it was first measured accurately in 1997 by Steve Lamoureux using plates separated by less than 1 micrometer. The observed force matched theoretical predictions to within experimental uncertainty, providing direct evidence that quantum fluctuations in vacuum carry real physical energy that can influence the behavior of matter. If quantum vacuum energy is real enough to move metal plates in laboratory experiments, then according to Einstein's general relativity, it should also curve spacetime and affect cosmic expansion. When physicists first attempted this calculation in the 1960s, they expected to find that vacuum energy might provide a small correction to cosmic evolution, perhaps helping to explain minor discrepancies between theoretical models and observations. Instead, they discovered a prediction so catastrophically wrong that it challenged the foundations of both quantum mechanics and general relativity. When you add up the energy contributions from quantum fluctuations in all possible quantum fields, throughout empty space, the result is an energy density that would cause the universe to expand so rapidly that atomic nuclei would be torn apart, preventing the formation of atoms, molecules, stars, or any complex structures. The magnitude of this discrepancy defies comprehension. The quantum field theory prediction for vacuum energy density exceeds observational limits by approximately 10,120. That is a 1 followed by 120 zeros. This mismatch is so severe that it suggests something fundamental is wrong with how we think about energy, gravity, or the nature of empty space. Either quantum field theory dramatically overestimates vacuum energy, or general relativity fails to correctly describe how vacuum energy affects spacetime curvature, or there exists some unknown mechanism that precisely cancels most of the vacuum energy contribution to cosmic expansion. Various theoretical proposals attempt to resolve this crisis, but none are entirely satisfactory. Supersymmetric theories suggest that every known particle has a superpartner with opposite quantum statistics, so that fermionic and bosonic contributions to vacuum energy exactly cancel. However, if supersymmetry exists in nature, it must be broken at energy scales we can currently probe, which means the cancellation cannot be exact and substantial vacuum energy contributions would remain. Other approaches propose that the vacuum energy we calculate in quantum field theory doesn't gravitate in the same way as ordinary matter and energy. Perhaps some unknown symmetry prevents vacuum fluctuations from contributing to the stress-energy tensor that appears in Einstein's equations. But such proposals require introducing new physics that has no independent experimental support. The most radical possibility is that our understanding of how energy curved spacetime breaks down when applied to quantum vacuum states. Einstein's general relativity was formulated to describe classical matter and energy distributions, and extending it to quantum systems might require modifications we haven't yet discovered. Some theories of quantum gravity suggest that spacetime itself emerges from more fundamental quantum interactions, making the question of how vacuum energy affects cosmic expansion ill-defined until we understand the quantum nature of gravity. String theory provides another perspective on the vacuum catastrophe by suggesting that what we call empty space is actually a complex landscape of higher dimensional geometries with enormous numbers of possible vacuum states. In this picture, the energy of any particular vacuum state is determined by the detailed geometry of extra dimensions that we cannot directly observe. Different regions of the universe might settle into vacuum states with different energy densities, creating a multiverse where the dark energy we observe is just one possibility among countless others. The anthropic principle offers a controversial interpretation of why our vacuum state has the specific dark energy density we observe. If an enormous number of different vacuum states exist throughout a cosmic multiverse, then most would have dark energy densities, either so large that they prevent structure formation or so negative that they cause rapid cosmic collapse. Only a tiny fraction would have dark energy densities compatible with the existence of stars, planets, and life. We observe the dark energy density we do simply because we exist in one of the rare regions where observers can evolve. But even if the anthropic explanation is correct, it doesn't solve the fundamental physics problem of why quantum field theory predictions are so catastrophically wrong. Understanding why vacuum energy doesn't gravitate as expected, or how unknown physics prevents it from dominating cosmic evolution, remains one of the deepest challenges in theoretical physics. Recent developments in quantum field theory and cosmology have revealed additional puzzles about the nature of vacuum states. Quantum entanglement experiments demonstrate that vacuum states contain correlated particle pairs that maintain instantaneous connections across arbitrary distances. These vacuum entanglements suggest that empty space possesses a rich quantum structure that might play important roles in cosmic evolution beyond simple energy density contributions. The holographic principle, developed from studies of black hole physics, proposes that all the information in any volume of space is encoded on its boundary surface. This suggests that the vacuum energy in any region might be fundamentally limited by the amount of information that can be processed on the boundary, providing a natural mechanism for preventing the vacuum catastrophe. However, applying holographic bounds to cosmology remains speculative and controversial. Dark energy observations have also revealed that whatever mechanism suppresses vacuum energy contributions must be extraordinarily fine-tuned. The observed dark energy density corresponds to approximately 10 to 29 grams per cubic centimeter, roughly 1 hydrogen atom per cubic meter of empty space. This value is small enough to allow structure formation in the early universe, but large enough to dominate cosmic evolution today, suggesting either incredible coincidence or unknown physics that dynamically adjusts vacuum energy as the universe evolves. The quantum mysteries surrounding dark energy thus illuminate fundamental gaps in our understanding of space, time, matter, and energy. Resolving the vacuum catastrophe will likely require revolutionary insights into the nature of quantum gravity, the structure of spacetime at the smallest scales, and the mechanisms that determine which quantum vacuum state describes our universe. These discoveries may ultimately reveal that dark energy is not an exotic new component of the cosmos, but rather a window into the deepest principles governing physical reality. Until we solve these quantum mysteries, dark energy remains our cosmic reminder that the universe operates according to principles we have barely begun to comprehend. Chapter 6. Scale Warfare. The cosmic battle between gravity and dark energy plays out differently at every scale, from the quantum realm to galaxy clusters, creating a complex hierarchy of forces that determines which effects dominate under different conditions. Understanding this scale-dependent warfare reveals why we do not notice dark energy in our daily lives, despite its control over the universe's ultimate fate. Consider what happens within an individual atom, where electromagnetic forces bind electrons to nuclei with energies measured in electron volts. At these scales, gravity is so weak that it is completely irrelevant. The gravitational attraction between an electron and proton is about 1039 times weaker than their electromagnetic attraction. Dark energy is even more negligible, exerting forces that are essentially zero over atomic distances. The quantum electromagnetic forces that determine atomic structure operate as if gravity and dark energy simply don't exist. Moving up in scale to molecules and chemical bonds, gravity remains utterly insignificant compared to electromagnetic forces. The covalent bonds that hold together complex molecules, like DNA, involve electromagnetic interactions between atoms that are trillions of times stronger than gravitational effects. Dark energy has influence over molecular distances is measured in forces smaller than 10 to 30 newtons, less than the weight of a single electron. At the scale of chemistry and biochemistry, electromagnetic forces reign supreme while gravity and dark energy are irrelevant. But as we progress to larger scales, the balance begins to shift. Within the human body, gravity becomes noticeable as the force that makes you feel your weight and determines which direction is down. However, it is still much weaker than electromagnetic forces. Your body is held together by electromagnetic interactions between atoms and molecules, not by gravitational attraction between different parts of your body. Dark energy remains undetectable over human body distances, exerting acceleration smaller than 10 to 30 meters per second squared. At the scale of planets and stars, gravity finally becomes the dominant force. The electromagnetic forces that bind individual atoms are overwhelmed by the collective gravitational attraction of countless particles acting together. A star like our Sun contains about YY atoms, and while each individual gravitational interaction is incredibly weak, the cumulative effect creates forces powerful enough to compress matter to densities and temperatures where nuclear fusion can occur. Dark energy still remains negligible within solar systems because gravitational binding energies exceed dark energy effects by enormous factors. The Earth's orbital velocity around the Sun is about 30 kilometers per second, maintained by gravitational attraction. that requires about YD joules of energy to overcome. Dark energy's effect on Earth's orbit amounts to an acceleration of less than 10 to 15 meters per second squared, so small that it would take longer than the age of the universe to measurably change orbital parameters. The situation becomes more complex when we examine galaxy-scale structures. The Milky Way contains approximately 100 billion stars with a total mass of about 1,042 kilograms, creating gravitational forces that bind the entire galaxy together despite the enormous distances involved. Dark matter, which outweighs ordinary matter by about 5 to 1, provides additional gravitational attraction that explains why spiral galaxies rotate faster than expected based on visible matter alone. Even at galactic scales, dark energy remains a minor player because galaxies are gravitationally bound systems where local gravitational attraction far exceeds the universal expansion rate. The Milky Way and Andromeda galaxies are actually approaching each other at about 110 kilometers per second despite cosmic expansion, because their mutual gravitational attraction overcomes the expansion of space between them. They will collide and merge in approximately 4.5 billion years, creating a combined elliptical galaxy that remains gravitationally bound despite universal acceleration. The transition point where dark energy begins to compete with gravity occurs at the scale of galaxy clusters, structures containing hundreds or thousands of individual galaxies bound together by gravity and dark matter. The largest galaxy clusters span about 10 million light-years and contain total masses exceeding 1,015 solar masses. At these scales, the competition between gravitational attraction and cosmic expansion becomes a close contest. Within galaxy clusters, gravity still wins because the matter density is much higher than the average cosmic density. The intracluster medium hot gas that fills the space between galaxies remains gravitationally bound despite cosmic expansion. Galaxy clusters continue to grow by accreting smaller groups and individual galaxies, demonstrating that gravity maintains its dominance over dark energy even at these enormous scales. But between galaxy clusters, dark energy finally gains the upper hand. The typical distance between major galaxy clusters is 100 to 200 million light-years, and at these separations, the density of matter and dark matter drops below the cosmic average. Dark energy density remains constant throughout space, so it becomes the dominant component determining how space evolves between clusters. This is where cosmic expansion manifests its effects most clearly. Galaxy clusters are moving away from each other with velocities that increase with distance, following Hubble's law. The space between clusters is expanding, carrying them apart faster than their mutual gravitational attraction can overcome. New galaxy clusters can no longer form in regions where dark energy dominates, because the expansion prevents matter from accumulating to the densities required for gravitational collapse. On the largest observable scales, hundreds of billions of light-years, dark energy wins the cosmic war decisively. The cosmic web of filaments and voids that characterizes large-scale structure reflects the balance between gravity and dark energy throughout cosmic history. Dense filaments mark regions where gravity successfully gathered matter despite cosmic expansion, while vast voids represent regions where dark energy prevented significant structure formation. The cosmic microwave background radiation provides a snapshot of this scale warfare from the early universe, when the cosmos was only 380,000 years old. At that epoch, matter density was much higher than today, while dark energy density remained the same, so gravity dominated cosmic evolution on all scales. The tiny temperature fluctuations in the cosmic microwave background trace density variations that would later grow under gravitational attraction to form the cosmic web we observe today. Computer simulations of cosmic evolution reveal how the balance has shifted over time. In the early universe, gravity could form structures on increasingly large scales as matter continued to collapse under its own attraction. But about 5 to 6 billion years ago, when the universe had expanded enough that matter density dropped below dark energy density, this process began to reverse. The largest structures that could form gravitationally had already formed, and dark energy began preventing the assembly of new large-scale structures. Future cosmic evolution will be dominated by dark energy's victory in this scale warfare. As the universe continues expanding and matter becomes increasingly dilute, dark energy's influence will extend to smaller and smaller scales. Galaxy clusters will eventually become isolated islands in an ever-expanding sea of empty space, unable to interact with each other as the distance between them grows beyond the range where gravity can operate effectively. On extremely long timescales, trillions of years in the future, dark energy may even overcome gravitational binding within galaxy clusters, though this depends on whether dark energy remains constant or evolves over time. If dark energy density increases, it can eventually overcome gravitational attraction on all scales, leading to a big rip scenario where even atoms are torn apart by cosmic expansion. The scale warfare between gravity and dark energy thus reveals that cosmic evolution is not a simple story of universal expansion, but a complex competition between forces that operate differently at different scales. This competition determines which structures can form and survive in an expanding universe, shaping the cosmic architecture from the smallest gravitationally bound systems to the largest voids between galaxy clusters. Understanding this warfare is crucial for predicting the long-term fate of all cosmic structures, including the future habitability of the universe for life and intelligence. Chapter 7. Future Isolation. The universe is embarking on a journey toward profound cosmic loneliness, where accelerating expansion will eventually isolate every galaxy cluster as a separate island in an infinite ocean of empty, expanding space. This future isolation represents one of the most melancholic consequences of dark energy's victory over gravity, fundamentally altering the nature of cosmic existence for any civilizations that might arise in the far future. Today, when we look out into the cosmos, we can observe galaxies stretching back nearly 13.8 billion years in time and space, revealing the entire history of cosmic evolution since the Big Bang. The Hubble Space Telescope and other instruments have mapped the distribution of galaxies out to distances where we see them as they existed when the universe was less than 1 billion years old. This cosmic perspective allows us to understand how structure formed and evolved throughout most of cosmic history. But this golden age of cosmic observability is temporary. Dark energy's acceleration means that space itself is expanding at an ever-increasing rate, and this expansion will eventually carry distant galaxies beyond our cosmic horizon, the boundary beyond which light cannot reach us, because space is expanding faster than light can travel. Once a galaxy crosses this horizon, it disappears from our observable universe forever, taking with it all information about its existence and evolution. The process has already begun. The most distant galaxies currently visible are receding from us at velocities that exceed 90% of light speed due to cosmic expansion. As dark energy continues accelerating the expansion, these galaxies will cross the cosmic horizon and vanish from view. The observable universe will gradually shrink, containing fewer and fewer galaxies as cosmic time progresses. Astrophysicist Lawrence Krauss calculated that in approximately 100 billion years, all galaxies beyond our local group, the gravitationally bound collection containing the Milky Way, Andromeda, and several dozen smaller galaxies will have disappeared beyond the cosmic horizon. Future astronomers living in this era will inhabit a cosmos that appears to contain only a single massive elliptical galaxy surrounded by empty space in all directions. This cosmic isolation will have profound implications for scientific discovery. Future civilizations will lose access to the observational evidence that allowed us to discover cosmic expansion, the Big Bang, and the existence of dark energy. The cosmic microwave background radiation will have redshifted to undetectable wavelengths. Distant supernovas will no longer be visible to serve as standard candles for measuring cosmic acceleration. The large-scale structure of the cosmic web will be completely invisible. Without these observational clues, future scientists may conclude that the universe consists of a single galaxy surrounded by infinite, static space, essentially returning to the cosmological worldview that Einstein and his contemporaries held before Hubble's discoveries. They will lack the evidence needed to infer that their universe is actually expanding, or that it began in a Big Bang, or that dark energy dominates cosmic evolution. This represents a profound loss of cosmic perspective. Our current understanding of the universe's history, composition, and ultimate fate depends critically on observations of distant galaxies and cosmic background radiation that will eventually become inaccessible. Future civilizations will inherit an impoverished cosmos where the grandest discoveries about cosmic evolution are no longer possible through direct observation. The isolation extends beyond observational astronomy to the fundamental physics of cosmic evolution. Today, gravity and dark energy compete on roughly equal terms within our cosmic neighborhood, allowing us to study both forces and understand their relative importance. But as dark energy's dominance grows stronger, future cosmic evolution will be determined almost entirely by dark energy effects, with gravity relegated to minor significance except within the most tightly bound systems. Galaxy clusters will become increasingly isolated as the expansion of space overwhelms their ability to interact gravitationally. The Coma cluster, currently about 320 million light-years away, is receding from us at approximately 7,000 kilometers per second due to cosmic expansion. As this recession velocity continues increasing, the cluster will eventually move so far away that light signals between our local group and Coma will no longer be able to overcome the expansion and reach their destination. This communication horizon creates a form of cosmic censorship where different regions of the universe become permanently disconnected from each other. Information, energy, and matter cannot be exchanged between sufficiently distant regions, effectively dividing the cosmos into separate, non-communicating domains. Each domain evolves independently, isolated from any knowledge of or influence from the others. The local group itself will undergo dramatic changes during this isolation process. The Milky Way and Andromeda galaxies are currently approaching each other and will collide in approximately 4.5 billion years, eventually merging to form a single elliptical galaxy that astronomers have dubbed Milkomeda. This merger will be one of the last major gravitational interactions in our cosmic neighborhood, as other nearby galaxies are carried away by cosmic expansion. Milkomeda will initially contain all the stars from both parent galaxies, roughly 200 billion solar masses of material that will continue fusing hydrogen and helium for hundreds of billions of years. But even this merged galaxy will face gradual isolation as cosmic expansion carries away the smaller satellite galaxies that currently orbit the local group. Eventually, Milkomeda will exist alone in an apparently infinite void. The long-term evolution of isolated galaxy systems like Milkomeda depends on processes that operate on much longer timescales than cosmic expansion. Stars will continue burning nuclear fuel, but the supply is finite. Red dwarf stars, which burn hydrogen very slowly, can maintain nuclear fusion for trillions of years. But even these longest-lived stars will eventually exhaust their fuel and fade to cold, dark remnants. Once star formation ceases due to depletion of interstellar gas, the galactic population will consist entirely of stellar remnants, white dwarf stars, neutron stars, and black holes. These objects will slowly evaporate through various quantum processes. White dwarfs will crystallize and cool to near absolute zero over timescales of 1,015 years. Protons may decay with a half-life of 1,034 years, causing even white dwarf remnants to gradually disappear. Black holes will persist the longest, evaporating through Hawking radiation on timescales that depend on their mass. Stellar mass black holes will evaporate in about YY years, while the supermassive black holes at galaxy centers will persist for 10,100 years or longer. Eventually, even these will disappear, leaving behind only elementary particles in an increasingly empty and cold universe. This far future cosmos will bear no resemblance to the rich, structured universe we observe today. No new stars will form, no galaxies will interact, no complex chemistry will occur. The isolated remnants of today's galaxy clusters will consist of cold, dark objects separated by vast expanses of empty space that continues expanding at accelerating rates. Yet even this desolate future scenario assumes that dark energy remains constant over cosmic time. If dark energy is not Einstein's cosmological constant, but rather a dynamic field that can evolve, the future could be even more dramatic. Phantom dark energy models predict that the acceleration could increase without limit, eventually overcoming gravitational binding on all scales, and tearing apart stars, planets, and even atomic nuclei in a catastrophic Big Rip. Alternatively, if dark energy weakens over time, gravity might eventually regain dominance and reverse cosmic expansion, leading to a big crunch, where all matter and energy collapse back together. Such scenarios would prevent the cosmic isolation described above, but at the cost of destroying all existing structures through either catastrophic acceleration or gravitational collapse. The profound isolation that awaits our cosmic future thus represents dark energy as ultimate victory over gravity and structure. While gravity succeeded in building the rich cosmic architecture of galaxies, stars, and planets that we observe today, dark energy will gradually dismantle this architecture by separating its components beyond any possibility of interaction. Future cosmic evolution will be dominated by the slow, inexorable decay of isolated systems in an ever-expanding, ever-emptying universe. This cosmic loneliness may seem deeply melancholic from our current perspective, but it also highlights the extraordinary privilege of our cosmic epoch. We live at precisely the moment in cosmic history when the universe reveals its greatest secrets, when distant galaxies remain visible, when cosmic background radiation preserves evidence of the Big Bang, and when the competition between gravity and dark energy creates the complex structures that make observation and understanding possible. Chapter 8. Spacetime Rebellion. The fabric of spacetime itself is rebelling against the very matter and energy it contains, stretching and accelerating in ways that seem to violate the fundamental principle that mass and energy should create gravitational attraction. This cosmic rebellion reveals that our understanding of spacetime as a passive arena for physical events is profoundly incomplete. Space itself is an active participant in cosmic evolution with properties that challenge everything we thought we knew about the nature of reality. Einstein's general relativity taught us that spacetime is not the fixed, absolute backdrop that Newton imagined, but a dynamic medium that responds to the presence of matter and energy. Massive objects curve spacetime, and this curvature manifests as what we experience as gravitational attraction. The more mass and energy present in a region, the more severely spacetime curves, creating stronger gravitational effects that pull matter together and resist expansion. This principle works perfectly for explaining the behavior of individual objects: planets orbiting stars, stars orbiting galaxy centers, galaxies falling toward each other in clusters. In every case we can directly observe, the curvature of spacetime creates attractive effects that bring matter together over time. Even exotic objects like black holes, where spacetime curvature becomes extreme, follow this pattern by attracting everything around them with such intensity that nothing can escape. But when we apply Einstein's equations to the universe as a whole, spacetime exhibits behavior that seems to contradict this fundamental principle. Instead of the attractive curvature that we observe locally, spacetime on cosmic scales curves in ways that drive matter apart with ever-increasing velocity. The same mathematical framework that perfectly describes gravitational attraction in solar systems and galaxies predicts cosmic repulsion that overwhelms gravitational effects across vast distances. This spacetime rebellion manifests most clearly in the accelerating expansion of cosmic distances. When astronomers measure the space between distant galaxy clusters, they find that this space is not just expanding, it's expanding at an accelerating rate that increases over time. Each cubic meter of space between clusters contains approximately 10 to 27 kilograms of dark energy, and this energy density remains constant even as space expands and creates more volume. The mechanism driving this rebellion involves properties of spacetime that have no analogy in our everyday experience. Unlike matter, which becomes more dilute as it spreads through expanding space, dark energy maintains constant density by creating more total energy as space expands. This violates our intuitive understanding of energy conservation, where the total amount of energy in any system should remain constant over time. But energy conservation in general relativity is more subtle than in classical physics. In an expanding universe, the concept of total energy becomes ambiguous because spacetime itself is evolving. The energy contained within any fixed volume of space can increase if that volume is expanding and contains a cosmological constant that represents energy inherent in space itself. This isn't a violation of fundamental conservation laws, but rather a consequence of how energy and spacetime interact in a dynamic universe. The mathematical description of this rebellion appears in the stress-energy tensor of Einstein's field equations, where dark energy contributes with negative pressure that is exactly equal in magnitude to its positive energy density. This combination creates gravitational effects with the opposite sign from ordinary matter. Instead of attracting surrounding objects, dark energy pushes them away by causing spacetime to expand around them. To understand how revolutionary this is, consider that every other form of matter and energy we know contributes to spacetime curvature in ways that create attractive gravitational effects. Electromagnetic radiation, despite being massless, still curves spacetime in ways that attract rather than repel. Even exotic forms of matter, predicted by particle physics theories, generally contribute positive energy density and positive or zero pressure, creating gravitational attraction. Dark energy stands alone as a form of energy that causes spacetime to curve in ways that drive objects apart rather than pull them together. This suggests that our catalog of possible forms of matter and energy is incomplete, missing fundamental types of energy that can exist in nature but have properties unlike anything we've encountered before. The rebellion extends beyond simple expansion to the very structure of spacetime at quantum scales. Quantum field theory predicts that empty space seethes with virtual particle pairs that appear and annihilate in timeframes shorter than direct observation can detect. These quantum fluctuations should contribute enormously to the energy density of vacuum, yet somehow their gravitational effects are either absent or precisely cancelled by unknown mechanisms. This quantum vacuum paradox suggests that spacetime rebellion operates at the deepest level of physical reality. Either our understanding of how quantum fields contribute to spacetime curvature is fundamentally wrong, or there exist quantum processes that prevent vacuum energy from gravitating in the same way as classical matter and energy. Both possibilities require revolutionary changes to our understanding of quantum gravity. Some theoretical approaches propose that spacetime itself emerges from more fundamental quantum processes, making the rebellion a consequence of the quantum information processing that creates the appearance of continuous spacetime from discrete quantum interactions. In these emergent gravity theories, what we interpret as dark energy might reflect the thermodynamic properties of the quantum processes that generate spacetime at the most fundamental level. String theory suggests another perspective on spacetime rebellion by proposing that our three-dimensional space is actually a lower-dimensional slice of a higher-dimensional space that contains additional dimensions we cannot directly observe. In these brand-neural models, dark energy might arise from interactions between our three-dimensional brain and other brains or bulk fields in higher dimensions, causing our space to accelerate, even though the total higher-dimensional spacetime follows conventional gravitational dynamics. The rebellion also manifests in the cosmic horizon problem, the fact that regions of the universe separated by distances larger than light could have traveled since the Big Bang nonetheless have nearly identical temperatures and properties. This suggests that spacetime itself underwent a period of exponential expansion, called cosmic inflation, in the earliest moments after the Big Bang, during which space expanded faster than light could travel and smoothed out initial irregularities. Cosmic inflation represents an earlier epoch of spacetime rebellion, driven by a different form of energy called the inflaton field that, like dark energy, cause repulsive gravitational effects and accelerated expansion. The fact that spacetime has rebelled against gravitational attraction at least twice in cosmic history, once during inflation and again during the current dark energy epoch, suggests that such rebellion might be a fundamental feature of cosmic evolution rather than an exotic anomaly. Modern observations reveal that spacetime rebellion is not a historical curiosity, but an ongoing, accelerating process that will determine the ultimate fate of cosmic structure. The space between galaxy clusters is expanding at rates that will eventually overcome gravitational binding even within clusters, potentially leading to a future where individual galaxies become isolated in an ever-expanding void. If the rebellion continues indefinitely, it will ultimately triumph over all other forces in the universe. Gravitational attraction that built stars, planets, and the complex structures necessary for life will be overwhelmed by spacetime's intrinsic tendency to expand and accelerate. The cosmic web of filaments and clusters that characterizes today's universe will dissolve into isolated remnants separated by vast expanses of empty, expanding space. Yet the most profound aspect of spacetime rebellion is what it reveals about the nature of space itself. Rather than being merely the passive stage on which physical events unfold, space possesses intrinsic properties that actively determine how matter and energy behave over cosmic distances and timescales. These properties, encoded in the cosmological constant or dark energy, represent aspects of physical reality that we have barely begun to understand. The rebellion of spacetime against matter thus stands as perhaps the greatest mystery in modern physics, challenging our most basic assumptions about the relationship between space, time, matter, and energy. Understanding why spacetime rebels and what this rebellion tells us about the fundamental nature of reality may require conceptual revolutions as profound as those that gave us quantum mechanics and general relativity. Chapter 9. True Boundaries. The universe possesses boundaries more fundamental than any physical barrier. Cosmic horizons, beyond which information cannot travel, where the very concept of causality breaks down, and where the fabric of spacetime itself determines what regions of reality can ever influence each other. These true boundaries reveal that cosmic expansion doesn't just separate objects in space. It creates permanent divisions in the structure of existence itself. Unlike the walls of a room or the surface of a planet, cosmic horizons are boundaries in spacetime that emerge from the finite speed of light combined with cosmic expansion. Light travels at exactly 299,792,458 meters per second in vacuum, the universe's ultimate speed limit for any form of information or causal influence. This speed seems enormously fast by human standards, but when combined with cosmic distances and expansion rates, it creates absolute limitations on which regions of the universe can ever communicate with each other. The most familiar cosmic horizon is our particle horizon. the boundary that defines the observable universe. Light from objects beyond this horizon has not had sufficient time to reach us since the Big Bang occurred 13.8 billion years ago. The current particle horizon lies approximately 46.5 billion light-years away, despite the universe's age of only 13.8 billion years, because space itself has been expanding while light travels toward us from distant sources. But dark energy creates a more profound and permanent type of boundary called the event horizon. While our particle horizon expands over time as light from increasingly distant objects reaches us, the event horizon represents regions from which light emitted today will never reach us in the future, no matter how long we wait. These regions are being carried away by cosmic expansion at rates that exceed light's ability to overcome the increasing distance. The mathematics of cosmic event horizons reveal their absolute nature. In a universe dominated by dark energy with constant density, the event horizon sits at approximately 16 billion light-years from any observer. Galaxies beyond this distance are receding so rapidly due to cosmic expansion that photons they emit today will never overcome the growing distance to reach any observer in our cosmic neighborhood. These galaxies are disappearing from our potential future light cone permanently. This creates a profound asymmetry in cosmic causality. We can observe galaxies that are currently beyond our event horizon because we're seeing light they emitted billions of years ago when they were closer to us. But we can never send signals to these galaxies or influence their evolution in any way, because any signal we transmit will be carried away by cosmic expansion before it can reach its destination. The existence of cosmic event horizons means that the universe is naturally dividing itself into causally disconnected regions that can never exchange information, energy, or matter. Each region evolves independently, following its own trajectory through cosmic time without any possibility of coordinating with distant regions or learning about their fate. Within our own causal region, the sphere defined by our event horizon, we can still observe the cosmic microwave background radiation and distant galaxies that provide information about cosmic evolution throughout most of universal history. But future observers will witness the gradual shrinkage of their observable universe as objects disappear beyond the event horizon and the cosmic microwave background redshifts to undetectable wavelengths. Stephen Hawking's work on black hole physics reveals deep connections between cosmic event horizons and the fundamental laws of thermodynamics. Just as black holes possess event horizons that define regions from which nothing can escape, and just as these horizons have temperatures and entropies proportional to their areas, cosmic event horizons also exhibit thermodynamic properties that suggest they contain fundamental information about the quantum structure of spacetime. The holographic principle, developed from studies of black hole information paradoxes, proposes that all information contained within any volume of space can be encoded on its boundary surface. Applied to cosmic horizons, this suggests that the maximum amount of information that can exist within our observable universe is determined by the area of our cosmic event horizon, not by the volume it encloses. This holographic bound implies that cosmic horizons represent fundamental limits not just on communication and causal influence, but on the total amount of information that can exist within any causal region of the universe. The apparent three-dimensional structure of space within our cosmic horizon might actually be a holographic projection of two-dimensional information encoded on the horizon's surface itself. Quantum mechanics adds another layer of mystery to cosmic boundaries through the phenomenon of quantum entanglement. Laboratory experiments demonstrate that quantum systems can maintain instantaneous correlations across arbitrary distances, seemingly violating the speed of light limitation that defines cosmic horizons. If particles become entangled and are then separated by cosmic expansion beyond the event horizon, do they maintain their quantum correlation despite being causally disconnected? Current understanding suggests that while quantum entanglement can exist across cosmic horizons, it cannot be used to transmit information faster than light. The correlations remain, but neither region can use them to send signals or coordinate their evolution. This preserves the fundamental structure of cosmic causality, while revealing that quantum mechanics operates according to principles that transcend classical spacetime boundaries. The cosmological multiverse hypothesis suggests that cosmic horizons might be temporary features of a much larger reality where different regions undergo different expansion histories. In eternal inflation models, the region we can observe represents just one bubble within an infinite expanse where new regions continuously undergo exponential expansion and create their own cosmic horizons. If the multiverse exists, then our cosmic horizon defines not the boundary of all reality, but merely the boundary of the region that shares our particular cosmic history. Beyond our horizon, other regions might have completely different physical laws, different values for fundamental constants, or even different numbers of spatial dimensions. Each region would be surrounded by its own cosmic horizon, creating an infinite hierarchy of causally disconnected domains. The anthropic principle offers one approach to understanding why we find ourselves within a cosmic region with particular properties. If the multiverse contains regions with all possible values for dark energy density, then most regions would either expand so rapidly that structure cannot form or collapse so quickly that complexity never develops. We observe the cosmic boundaries we do because we exist in one of the rare regions where expansion proceeds at rates compatible with the formation of stars, planets, and life. But even within our own cosmic region, dark energy's acceleration means that our effective cosmic boundaries are shrinking over time. The event horizon remains at approximately the same distance, but the number of galaxies within this horizon decreases as cosmic expansion carries distant objects beyond the boundary. Future civilizations will inhabit a cosmos with increasingly restrictive boundaries that limit their access to information about cosmic evolution and structure. Looking toward the far future, cosmic boundaries will eventually isolate individual galaxy clusters as separate domains that cannot communicate with each other. The local group of galaxies will merge into a single elliptical galaxy surrounded by empty space extending to the cosmic horizon. Observers in this future cosmos will face absolute boundaries that prevent them from learning about the existence of other galaxies, other civilizations, or even the expansion history that created their isolation. These true boundaries thus represent more than geometric features of spacetime. They define the ultimate limits of knowledge, influence, and even existence itself. The cosmic horizons created by dark energy's acceleration establish permanent divisions in reality that no future technology can overcome, no matter how advanced. They create a cosmos where vast regions evolve in complete isolation, following separate trajectories toward futures that can never be coordinated or even observed from distant regions. The profound implication is that the universe naturally fragments into disconnected domains where different evolutionary paths unfold independently. Our current ability to observe cosmic structure across billions of light years represents a temporary phase in cosmic evolution, destined to give way to increasing isolation as dark energy's influence grows stronger over time. Understanding these true boundaries reveals both the privilege of our current cosmic perspective and the ultimate loneliness that awaits any civilization surviving into the universe's distant future. Chapter 10. Ultimate Victory Dark. Energy's triumph over gravity represents not just a temporary phase in cosmic evolution, but the ultimate destiny of everything that exists. A victory so complete that it will reshape the meaning of structure, organization, and existence itself on scales that dwarf our current comprehension. This ultimate victory reveals that the universe is fundamentally dedicated to dissolution rather than construction, to separation rather than unity, to increasing entropy and isolation rather than growing complexity, and connection. The mathematics of cosmic evolution predict that dark energy's dominance will only grow stronger with time. As the universe expands and matter becomes increasingly dilute, the energy density of normal matter and dark matter decreases while dark energy density remains constant. Today, dark energy comprises approximately 68% of the universe's total energy content. In the future, as matter density continues declining, dark energy will approach 100% dominance, making cosmic acceleration the only significant force affecting large-scale evolution. This growing dominance means that gravity's ability to build and maintain cosmic structures will be systematically dismantled. Galaxy clusters, the largest gravitationally bound structures in the universe, will be torn apart as cosmic expansion accelerates to rates that overcome the gravitational forces holding them together. Individual galaxies will become isolated islands in an ever-expanding ocean of empty space, unable to interact with or even observe each other. The timeline of this victory unfolds over scales that challenge human comprehension. Within the next 100 billion years, all galaxies beyond our local group will disappear beyond the cosmic horizon, carried away by expansion to distances so great that light can no longer bridge the gap. The local group itself will merge into a single massive elliptical galaxy, but even this structure faces eventual dissolution if dark energy's influence continues growing. Computer simulations of far future cosmic evolution reveal the stages of dark energy's ultimate victory. First, galaxy clusters dissolve as expansion overpowers gravitational binding between their member galaxies. Then galaxy groups separate as space expansion accelerates beyond the escape velocity of loosely bound galactic associations. Finally, if dark energy density increases over time rather than remaining constant, even tightly bound systems like individual galaxies could be torn apart in a catastrophic Big Rip scenario. The Big Rip represents dark energy's most complete possible victory, a future where accelerating expansion becomes so extreme that it overcomes not just gravitational forces, but all fundamental forces that create structure in nature. In these models, cosmic acceleration eventually grows strong enough to tear apart galaxy clusters in about 22 billion years. Individual galaxies in 60 million years before the rip, solar systems in 3 months before the rip, planets in 30 minutes before the rip, and finally atomic nuclei in the last fraction of a second. Even if dark energy remains constant rather than growing stronger, its victory over gravity will reshape the cosmos beyond recognition. Stars will continue burning nuclear fuel for hundreds of billions of years in isolated galaxies, but eventually all stellar fuel will be exhausted and no new stars can form. The universe will enter a degenerate era where stellar remnants, white dwarfs, neutron stars, and black holes constitute the only remaining compact objects. Dark energy's victory extends beyond the destruction of large-scale structure to the fundamental thermodynamic evolution of the universe. Cosmic expansion driven by dark energy increases the total volume of space while spreading matter and energy across increasingly larger regions. This process maximizes entropy, the universe's tendency toward disorder and thermal equilibrium, by ensuring that energy density approaches zero everywhere. The second law of thermodynamics guarantees that entropy must increase over time in any closed system, and dark energy provides the mechanism that drives this increase on cosmic scales. By accelerating cosmic expansion, dark energy ensures that the universe evolves toward a state of maximum entropy, where no energy gradients remain to power complex processes or sustain organized structures. This thermodynamic victory has profound implications for the long-term survival of life and intelligence. Complex biological and technological systems require energy gradients to maintain their organization and perform useful work. As cosmic expansion driven by dark energy eliminates these gradients by spreading energy uniformly throughout space, The universe approaches a state where no complex processes can operate. Yet, even in this victory, dark energy faces its own ultimate limitation through quantum mechanics. Stephen Hawking's discovery of black hole evaporation revealed that even the most extreme gravitational systems cannot maintain their structure indefinitely. Black holes emit thermal radiation and gradually evaporate, with smaller black holes evaporating faster than larger ones. Stellar mass black holes will disappear in about years, while supermassive black holes at galaxy centers will persist for 10,100 years before finally evaporating. The evaporation of black holes represents the universe's final triumph over gravity, the complete elimination of the most extreme gravitational structures that can exist in nature. After all black holes disappear, the cosmos will contain only elementary particles in thermal equilibrium, separated by vast distances in ever-expanding space. This represents dark energy's ultimate victory, a universe where gravitational attraction has been completely overcome and only the smooth expansion of empty space continues. But quantum mechanics introduces fundamental uncertainties into this ultimate victory through the possibility of quantum fluctuations that could spontaneously create new structures. In the far future universe dominated by dark energy, random quantum events could occasionally produce density fluctuations large enough to collapse under their own gravity and form new black holes. These quantum black holes would then evaporate through Hawking radiation, creating temporary islands of structure in otherwise empty cosmos. The statistical mechanics of quantum fluctuations in de Sitter space, the geometry of a universe dominated by constant dark energy, predict that these spontaneous structure formation events will occur with calculable probabilities over extremely long timescales. Quantum mechanics thus ensures that dark energy's victory over gravity cannot be absolutely complete, though the intervals between structure formation events will exceed 10,100 years by enormous factors. Some cosmological models propose that dark energy's ultimate victory might be temporary rather than permanent. If dark energy is not Einstein's cosmological constant, but rather a dynamic field that can evolve over time, it might weaken in the far future and allow gravity to regain dominance. Such scenarios could lead to renewed structure formation, cosmic collapse, or cyclic models where the universe alternates between expansion and contraction phases. The episodic and cyclic cosmology models suggest that dark energy's current victory might be part of a larger cycle where the universe undergoes periods of accelerated expansion, followed by phases of gravitational collapse and renewed structure formation. In these models, dark energy's dominance represents just one stage in an eternal cosmic cycle that includes both expansion and contraction phases. Alternative theories of gravity also challenge the inevitability of dark energy's ultimate victory by proposing that gravitational physics might operate differently on cosmic scales than within solar systems and galaxies. Modified gravity theories suggest that what we interpret as dark energy might actually represent the breakdown of Einstein's general relativity at extremely large distances, with gravity becoming repulsive rather than attractive beyond certain length scales. If modified gravity theories are correct, then the cosmic acceleration we observe might not require any exotic form of energy at all, but could emerge naturally from the geometry of spacetime itself. In some modified gravity models, the accelerated expansion is a temporary phase that will eventually give way to renewed gravitational attraction and possible cosmic collapse. Yet regardless of the specific mechanism driving cosmic acceleration, current observations confirm that dark energy or its equivalent is winning the cosmic battle against gravity. The acceleration has persisted for billions of years and shows no signs of weakening. Galaxy formation has effectively ceased in regions where dark energy dominates, and the large-scale structure of the universe has transitioned from growth to gradual dissolution. Dark energy's ultimate victory thus represents the culmination of cosmic evolution, the point at which the universe's tendency toward maximum entropy overcomes all forces that create and maintain organized structures. This victory reveals that our current epoch, where gravity and dark energy compete on roughly equal terms, represents a brief moment of balance in a cosmos ultimately destined for dissolution and isolation. Understanding this ultimate victory provides cosmic perspective on the temporary nature of all structure and organization. From individual atoms to galaxy clusters, every organized system exists only because cosmic expansion has not yet progressed far enough for dark energy to overcome the forces that bind these systems together. In the deep future, dark energy's victory will be so complete that the very concepts of structure, complexity, and organization will lose their meaning in a universe composed only of elementary particles in thermal equilibrium across infinite, empty space. Chapter 11. Cosmic Acceptance. Perhaps the most profound truth about our universe is that it demands we accept paradox as the fundamental nature of reality. That the same cosmos which brought forth stars, planets, life, and consciousness through gravitational attraction is simultaneously dedicated to undoing all of this through accelerated expansion driven by forces we barely understand. This cosmic acceptance requires embracing a universe that is neither purely constructive nor purely destructive, but paradoxically both, operating according to principles that transcend our everyday intuitions about causation, purpose, and meaning. The classical worldview promised a cosmos of logical consistency where causes led to predictable effects, where forces operated according to comprehensible principles, and where the universe followed rational patterns that human intelligence could eventually decode. Newton's mechanics suggested a clockwork cosmos where gravitational attraction governed everything from planetary orbits to cosmic structure according to simple, elegant laws. Even Einstein's relativity, despite its revolutionary implications, maintained the promise of mathematical beauty and conceptual coherence underlying physical reality. Dark energy shatters this promise of rational comprehensibility. Here is a phenomenon that dominates cosmic evolution, yet resists explanation within our most successful theoretical frameworks. Quantum field theory predicts vacuum energy densities 120 orders of magnitude larger than observed dark energy effects, creating what physicists call the worst prediction in the history of science. General relativity describes dark energy's effects with mathematical precision, but offers no insight into what this energy actually represents or why it exists. This failure of our most fundamental theories to explain the dominant component of cosmic evolution forces us to confront the possibility that the universe operates according to principles that exceed human conceptual capacity. Perhaps the assumption that reality must conform to patterns accessible to human reason represents intellectual hubris rather than justified confidence. The cosmos may be under no obligation to satisfy our desire for logical consistency and complete understanding. Yet cosmic acceptance doesn't require abandoning scientific inquiry or embracing mystical resignation. Instead, it calls for intellectual humility that acknowledges the provisional nature of all human knowledge while maintaining commitment to empirical investigation and theoretical development. We can measure dark energy's effects, map its influence on cosmic evolution, and predict its consequences for the future without needing to understand its fundamental nature or ultimate purpose. This perspective transforms dark energy from an embarrassing theoretical failure into a profound invitation for intellectual growth. The phenomenon challenges us to develop new conceptual frameworks that can accommodate aspects of reality that transcend current understanding. Perhaps consciousness itself represents a form of complexity that emerges precisely because the universe contains inexplicable elements that resist complete reduction to mechanical processes. The interplay between gravity and dark energy reveals a cosmos of extraordinary creativity and destruction operating simultaneously on cosmic scales. Gravity builds the hierarchical structures of cosmic architecture, from planetary systems to galaxy clusters, creating environments where complex chemistry, biological evolution, and consciousness can emerge. Dark energy simultaneously works to dissolve these structures, ensuring that all organized systems remain temporary and that the universe trends toward maximum entropy and isolation. This dual nature suggests that the universe is fundamentally committed to exploring all possibilities rather than optimizing for any particular outcome. Gravity creates temporary islands of complexity where novel phenomena can emerge and evolve, while dark energy ensures that these islands remain temporary so that space remains available for different configurations to arise. The cosmos appears dedicated to experimentation rather than permanence, to diversity rather than stability. From this perspective, the apparent conflict between gravitational construction and dark energy dissolution represents creative tension rather than tragic contradiction. Life, consciousness, and technological civilization emerged during the brief cosmic epochs when these forces achieve temporary balance, creating environmental conditions complex enough to support organized systems, yet stable enough to allow their development over geological and biological timescales. Our current cosmic epoch represents exactly such a moment of creative balance. Dark energy has become dominant enough to halt the formation of new large-scale structures, preventing the universe from continuing to build ever larger gravitationally bound systems. But this dominance is not yet strong enough to destroy existing structures like galaxy clusters, individual galaxies, and stellar systems. We inhabit a cosmic sweet spot where maximum complexity coexists with the beginning of universal dissolution. This temporal positioning suggests that consciousness might naturally arise during cosmic epochs, characterized by the transition from gravitational dominance to dark energy dominance. Complex systems require the stable platforms created by gravitational attraction, but they also benefit from the dynamic, evolving environment created by cosmic expansion. Too little expansion, and the universe becomes static and unchanging. Too much expansion, and complex structures cannot form or maintain themselves. The anthropic principle offers one framework for understanding this coincidence. If consciousness can only emerge during cosmic epochs, when gravity and dark energy achieve temporary balance, then conscious observers will naturally find themselves living during exactly the period when these forces compete on equal terms. The apparent fine-tuning of cosmic evolution to produce conscious beings reflects observational selection rather than cosmic design. But cosmic acceptance transcends anthropic reasoning to embrace the fundamental mystery of existence itself. Why should there be anything rather than nothing? Why should physical laws exist that permit complex structures to arise? Why should consciousness emerge that can contemplate its own cosmic context and mortality? These questions may represent the deepest inquiries possible for minds embedded within the reality they attempt to understand. Dark energy confronts us with the ultimate question of cosmic meaning in a universe apparently dedicated to dissolution rather than permanent achievement. If all structures are temporary, if all complexity faces eventual destruction, if consciousness itself will disappear when the last stars burn out and the final black holes evaporate, then what significance can we attribute to our brief existence in cosmic history? One response emphasizes the intrinsic value of the experience itself, independent of its duration or ultimate fate. Conscious beings represent the universe's remarkable ability to understand itself, even temporarily. Through scientific investigation, artistic creation, moral development, and spiritual inquiry, consciousness transforms meaningless matter and energy into systems capable of knowledge, beauty, ethics, and transcendence. The fact that these achievements are temporary doesn't diminish their reality or significance. Another response focuses on the role of consciousness in cosmic evolution itself. Perhaps the emergence of intelligence represents a phase transition in the universe's development, where matter becomes organized in ways that can influence cosmic evolution through technology and intentional action. Advanced civilizations might develop capabilities to harness dark energy, manipulate cosmic expansion, or create pocket universes with different physical laws and evolutionary trajectories. From this perspective, the current competition between gravity and dark energy represents the background conditions necessary for intelligence to emerge, but not the final chapter in cosmic evolution. Conscious beings might eventually transcend the limitations imposed by dark energy's victory over gravity, creating new forms of organization and complexity that operate according to different principles than those governing purely physical processes. Yet cosmic acceptance ultimately requires embracing uncertainty about such possibilities while finding meaning and purpose in the immediate reality of conscious existence within a universe that permits our existence even as it guarantees our ultimate impermanence. This acceptance doesn't demand resignation or despair, but rather a form of cosmic humility that acknowledges our participation in processes vastly exceeding our control or complete understanding. The profound gift of cosmic acceptance is the recognition that consciousness represents an extraordinary phenomenon, regardless of its ultimate fate. We exist as temporary organizations of matter and energy that can contemplate the cosmos, understand physical laws, create beauty and meaning, and experience wonder at the mystery of existence itself. These capacities emerge from the same cosmic processes that will eventually lead to our dissolution, suggesting that the universe is capable of creating phenomena that transcend the mechanical processes from which they arise. This transcendence doesn't require supernatural explanations or denial of physical reality. Instead, it recognizes that consciousness represents an emergent property of cosmic evolution that introduces qualitatively new categories of existence, knowledge, beauty, ethics, meaning, and purpose that have no direct analogs in purely physical processes. Cosmic acceptance thus involves embracing both our complete dependence on physical processes and our partial independence from reduction to those processes alone. Living with cosmic acceptance means finding profound meaning in temporary existence within a cosmos dedicated to exploration rather than permanence. It means pursuing knowledge, creating beauty, developing wisdom, and expressing love while acknowledging that all these achievements will eventually disappear as dark energy's victory becomes complete. This paradoxical existence, meaningful yet impermanent, significant yet temporary, may represent the deepest truth about conscious participation in cosmic evolution. Chapter 12. Beyond Understanding. The ultimate lesson of dark energy's cosmic triumph may be that the universe operates according to principles that exist beyond the boundaries of human understanding, challenging us to embrace mystery as a fundamental feature of reality rather than a temporary limitation of our knowledge. This recognition doesn't represent defeat for scientific inquiry, but rather its deepest success, revealing the profound depths of cosmic reality that extend far beyond what any finite intelligence can completely comprehend. Throughout human intellectual history, each major scientific revolution has expanded our understanding while simultaneously revealing new layers of mystery. Newton's mechanics explained planetary motion, but introduced the puzzle of gravitational action at a distance. Einstein's relativity resolved this puzzle, but created new enigmas about the nature of spacetime and quantum gravity. Quantum mechanics provided unprecedented predictive power while raising fundamental questions about measurement, reality, and the relationship between observation and existence. Dark energy continues this pattern by providing precise mathematical descriptions of cosmic acceleration while revealing our profound ignorance about 68% of the universe's contents. We can measure its effects with extraordinary accuracy, predict its influence on future cosmic evolution, and incorporate its properties into cosmological models that match observations with remarkable precision. Yet we have no compelling theoretical explanation for why it exists, what it actually represents, or how it relates to other fundamental aspects of physical reality. This knowledge-ignorance paradox suggests that the universe may be structured in ways that systematically exceed human cognitive capacity. Our brains evolved to understand environmental patterns relevant for survival and reproduction in terrestrial ecosystems over timescales ranging from seconds to decades. The fact that these same cognitive capacities can extend to comprehend stellar evolution, galactic dynamics, and cosmic expansion represents an extraordinary achievement that was never guaranteed by evolutionary processes. But perhaps there exist aspects of reality that require forms of understanding fundamentally different from those accessible to biological intelligence shaped by evolutionary selection pressures. Dark energy might represent one such aspect, a cosmic phenomenon that operates according to principles requiring conceptual frameworks that exceed what neural networks optimized for terrestrial survival can develop. The mathematics of dark energy provides partial insight into these transcendent principles. Einstein's field equations describe how dark energy curves spacetime in ways that drive cosmic acceleration, but the equations themselves represent symbolic relationships rather than intuitive understanding. We can manipulate the symbols, calculate their implications, and use them to make testable predictions without necessarily comprehending what they mean in terms of deeper physical reality. This symbolic mathematical understanding might represent the closest approach to cosmic truth available to minds like ours. Rather than seeking complete conceptual comprehension, scientific inquiry can focus on developing increasingly sophisticated mathematical frameworks that capture natural patterns with greater accuracy and broader scope. The success of such frameworks in predicting observations demonstrates their connection to reality, even when they exceed our capacity for intuitive understanding. Quantum mechanics already demonstrates this approach by providing extraordinarily successful predictions about atomic and subatomic phenomena through mathematical formalism that resists intuitive interpretation. No one truly understands why quantum superposition, entanglement, or measurement collapse occur. Yet the mathematical framework describes these phenomena with unprecedented precision. Dark energy might simply extend this pattern to cosmological scales. The possibility that fundamental aspects of reality exceed human understanding also raises profound questions about the nature and limitations of consciousness itself. If conscious minds represent local organizations of matter and energy that can understand aspects of the cosmic processes from which they emerge, then perhaps consciousness operates within inherent boundaries determined by its physical substrate and evolutionary history. Alternatively, consciousness might represent a cosmic phenomenon with capacities that exceed those demonstrated by current human intelligence. Advanced civilizations might develop forms of understanding that transcend the limitations of biological cognition through technological enhancement, artificial intelligence, or integration with cosmic processes we cannot currently imagine. From this perspective, our inability to comprehend dark energy might reflect the preliminary nature of human consciousness, rather than absolute limitations of mind in general. The search for extraterrestrial intelligence takes on new significance when viewed through this lens. Contact with alien civilizations that evolved under different conditions might provide access to forms of understanding that could illuminate aspects of reality, like dark energy, that remain opaque to human cognition. Such civilizations might have developed scientific frameworks that transcend our current theoretical limitations, offering insights into cosmic phenomena that we can observe but cannot explain. Yet even perfect theoretical understanding of dark energy's physical nature might not eliminate its essential mystery. The deepest questions about cosmic reality concern not just how natural processes operate, but why they exist at all. Why should there be physical laws that permit complex structures to arise? Why should consciousness emerge that can contemplate cosmic evolution? Why should reality possess mathematical structure accessible to finite minds? These ontological questions about the existence and nature of reality itself may represent permanent mysteries that exceed any possible form of understanding. The fact that we can ask such questions demonstrates remarkable properties of consciousness, but it doesn't guarantee that satisfactory answers exist or could be comprehended if they did exist. Some aspects of reality might be inherently beyond understanding for any finite intelligence, regardless of its sophistication. Dark energy thus confronts us with what we might call cosmic humility, recognition that our scientific achievements, remarkable as they are, represent early steps in exploring a reality that extends far beyond our current comprehension. This humility doesn't discourage continued inquiry, but rather motivates it by suggesting that every answer reveals new questions and every explanation illuminates deeper mysteries. Living with such cosmic humility requires developing comfort with fundamental uncertainty while maintaining commitment to empirical investigation and theoretical development. We can continue measuring dark energy's effects, testing cosmological models, and developing new theoretical frameworks without needing to believe that complete understanding is either possible or necessary for meaningful scientific progress. This approach also transforms our relationship to cosmic existence itself. Rather than seeking to control or fully comprehend our cosmic context, we can learn to participate consciously in processes that transcend our understanding while finding meaning in that participation. Consciousness becomes a way of engaging with cosmic mystery rather than a tool for eliminating it. The profound gift of recognizing reality's transcendence of human understanding is the opening it creates for wonder, awe, and reverence in response to cosmic existence. When we acknowledge that dark energy represents aspects of reality that we may never fully comprehend, we create space for experiencing our cosmic context as fundamentally mysterious and extraordinary rather than merely complicated. This perspective doesn't require abandoning rational inquiry or embracing supernatural explanations. Instead, it suggests that rational inquiry, pursued with sufficient depth and breadth, naturally leads to recognition of its own limitations and to appreciation for the mystery within which all understanding operates. Science becomes a practice of approaching cosmic transcendence through empirical investigation, rather than a method for eliminating mystery through complete explanation. Dark energy's resistance to theoretical understanding thus serves as a cosmic invitation to develop new forms of relationship with reality that integrate rigorous empirical investigation with humble recognition of cognitive limitations. We can simultaneously pursue the most sophisticated possible scientific understanding while acknowledging that this understanding will always occur within a larger context of cosmic mystery that exceeds our capacity for complete comprehension. Perhaps this integration represents consciousness's highest potential, not the achievement of omniscience, but the development of wisdom that knows both the power and the limits of knowledge, finding profound meaning in conscious participation within cosmic processes that forever exceed complete understanding. Dark energy becomes not just a cosmological phenomenon, but a mirror reflecting the fundamental mystery of existence itself, challenging us to embrace our role as conscious participants in a universe far more wondrous and incomprehensible than we ever imagined. This recognition transforms the question, why is the universe expanding, into a deeper inquiry. What does it mean to be conscious beings capable of wonder within a cosmos that systematically exceeds our understanding? The answer may lie not in solving cosmic mysteries, but in learning to live meaningfully within them. Throughout this journey, we've discovered that gravity's apparent failure to prevent cosmic expansion reveals not weakness in gravitational theory, but rather the extraordinary nature of the universe we inhabit. We've uncovered how dark energy dominates cosmic evolution despite being completely invisible to direct detection. We've explored how quantum vacuum energy should theoretically cause expansion rates trillions of times faster than observed, creating what physicists call the worst prediction in scientific history. Most remarkably, we've seen how cosmic acceleration will ultimately triumph over gravitational attraction, leading to a future where every galaxy becomes an isolated island in an ever-expanding ocean of empty space. But perhaps the most profound insight is how this cosmic tug-of-war reveals that the universe operates according to principles that systematically exceed human understanding, challenging us to find meaning within mystery rather than seeking complete comprehension of cosmic processes. The same forces that will eventually dissolve all cosmic structure also create the temporary conditions that allow complexity, life, and consciousness to emerge and contemplate their own cosmic context. As you continue living your daily life after watching this, remember that every breath you take occurs within a universe where space itself is rebelling against the matter it contains, where invisible energy dominates cosmic evolution, and where forces beyond our comprehension determine the ultimate fate of everything that exists. When you look up at the night sky, you're observing galaxies that are already being carried away by cosmic expansion, many of which will disappear beyond our cosmic horizon within the next 100 billion years. The space between you and those distant stars is expanding right now, creating new volume filled with dark energy that drives further acceleration. Every cubic meter of seemingly empty space around you contains enough dark energy to power human civilization. Yet this energy is so evenly distributed and so resistant to extraction that we cannot harness it or even understand what it actually represents. You exist within an ocean of invisible energy that is simultaneously everywhere and nowhere, detectable only through its effects on the largest scales of cosmic architecture. When you consider the gravitational forces that hold Earth in orbit around the Sun, that bind the solar system within our galaxy, and that maintain the structural integrity of galaxy clusters across cosmic distances, remember that these same forces are gradually losing their cosmic battle against dark energy's relentless acceleration. The universe is not becoming more gravitationally bound over time, but less so, as space expansion overcomes the attractive forces that built the cosmic web in the first place. This cosmic perspective transforms everyday experiences with profound meaning. The fact that you can think, feel, love, and contemplate your existence represents an extraordinary achievement that emerges from temporary conditions created by the competition between cosmic forces. Gravity provided the stable platforms necessary for complex chemistry, biological evolution, and the emergence of consciousness, while cosmic expansion powered by dark energy created the dynamic, evolving environment within which these processes could unfold. Your consciousness represents the universe's remarkable ability to understand itself, even temporarily, even incompletely. Through scientific investigation, you participate in cosmic processes that transcend your individual existence, contributing to the accumulated knowledge that reveals the universe's structure, history, and destiny. Every measurement of cosmic expansion, every observation of distant galaxies, every theoretical insight into dark energy represents consciousness engaging with cosmic reality in ways that transform meaningless matter and energy into understanding, beauty, and meaning. Yet this achievement occurs within a cosmic context that guarantees its impermanence. The accelerating expansion driven by dark energy ensures that the environmental conditions supporting complex life will eventually disappear as the universe evolves toward increasing isolation and entropy. All stars will burn out, all black holes will evaporate, and all complex structures will dissolve into elementary particles separated by vast distances in ever-expanding space. This cosmic destiny doesn't diminish the significance of consciousness or the meaning of human existence, but rather illuminates their extraordinary nature. You exist as a temporary organization of matter and energy that can experience wonder, pursue truth, create beauty, express love, and contemplate the mystery of existence itself. These capacities emerge from cosmic processes while transcending reduction to purely mechanical interactions, suggesting that consciousness represents a qualitatively different form of cosmic phenomenon. The profound gift of understanding dark energy's cosmic dominance is the perspective it provides on the relationship between permanence and meaning. Nothing in the cosmos persists forever, yet temporary phenomena can possess significance that exceeds their duration. The stars that will eventually burn out have created the chemical elements necessary for biological complexity. The galaxies that will drift apart in cosmic isolation have provided the environments where planetary systems and life could develop. The gravitational structures that dark energy will ultimately dissolve have created the conditions where consciousness could emerge to contemplate cosmic evolution. You are not separate from these cosmic processes, but rather a temporary manifestation of the universe's capacity for self-awareness. The atoms in your body were forged in stellar cores and distributed throughout space by supernova explosions. The energy that powers your thoughts derives ultimately from nuclear fusion in the sun's core. The gravitational forces that maintain Earth's stable environment also bind galaxy clusters across billions of light years. The dark energy that will determine cosmic destiny operates through the same spacetime that enables your existence. This cosmic integration means that understanding dark energy and cosmic expansion provides insight not just into astronomical phenomena, but into the fundamental nature of your own existence within cosmic evolution. You represent a way that the universe has organized itself to comprehend its own structure and destiny, a temporary arrangement of cosmic materials that can contemplate permanence and impermanence, meaning and mystery, understanding and transcendence. The question that confronts every conscious being in a universe dominated by dark energy is how to find meaning within cosmic processes that guarantee the impermanence of all achievements. Perhaps the answer lies not in seeking permanent accomplishments, but in appreciating the extraordinary fact that temporary organizations of matter and energy can experience beauty, pursue knowledge, express compassion, and contribute to the universe's ongoing exploration of its own possibilities. Your brief existence occurs during a remarkable cosmic epoch when the competition between gravity and dark energy creates environmental conditions complex enough to support consciousness, yet dynamic enough to stimulate continuous development and change. This temporal positioning represents an extraordinary privilege. You live during the era when the universe reveals its greatest secrets through observations of cosmic microwave background radiation, distant supernovas, and large-scale structure formation. Future civilizations, if any survive into the far future, will inhabit a cosmos where most evidence for cosmic evolution has disappeared beyond observable horizons. They will lack access to the discoveries that reveal cosmic expansion, dark energy, and the Big Bang origin of cosmic structure. Your cosmic perspective includes knowledge about universal history and destiny that may be inaccessible to conscious beings in other cosmic epochs. This temporal privilege creates responsibility as well as opportunity. The knowledge that consciousness has accumulated about cosmic evolution, the beauty that it has created in response to cosmic mystery, and the wisdom that it has developed about living meaningfully within impermanent conditions represent achievements that could influence cosmic evolution through the choices that conscious beings make about their future development. Advanced civilizations might eventually develop technologies that can harness dark energy, manipulate cosmic expansion, or create pocket universes with different physical laws and evolutionary trajectories. Such capabilities would transform consciousness from a passive observer of cosmic evolution into an active participant that can influence the universe's destiny. The current competition between gravity and dark energy might represent only the background conditions necessary for intelligence to emerge, not the final chapter in cosmic development. Yet even if consciousness ultimately transcends the limitations imposed by dark energy's cosmic dominance, the fundamental mystery of existence itself will likely persist. Why should there be anything rather than nothing? Why should consciousness emerge that can contemplate cosmic reality? Why should temporary organizations of matter and energy be capable of experiencing meaning, beauty, and transcendence? These questions may represent the deepest inquiries possible for any finite intelligence, regardless of its technological capabilities or cosmic influence. They point toward aspects of reality that forever exceed complete understanding, suggesting that mystery represents a permanent feature of existence rather than a temporary limitation of knowledge. The ultimate gift of cosmic perspective is the recognition that you participate in processes vastly greater than individual comprehension while possessing capacities that transcend reduction to mechanical causation. You exist within cosmic mystery while contributing to the universe's ongoing exploration of its own possibilities through consciousness, creativity, and the pursuit of meaning within impermanence. If you made it this far through our cosmic journey, subscribe and give this video a thumbs up. The universe's expansion is accelerating, but our understanding of it doesn't have to remain static. Check out my video on quantum mechanics and consciousness. I'm sure you'll find it illuminates even deeper mysteries about the nature of reality itself. In the end, the question, if gravity pulls everything together, why is the universe expanding, leads us to the most profound recognition possible. We exist as temporary arrangements of cosmic materials that can contemplate permanence and impermanence, understanding and mystery, meaning and transcendence within a universe dedicated to exploring all possibilities rather than achieving any permanent state. This may be the deepest truth about cosmic existence, that it creates temporary windows of consciousness through which the universe can experience wonder at its own extraordinary and inexplicable nature.